So yesterday, we were talking about vertical circular motion. Okay? And what we said was that for a vertical circle, the centripetal force is our net force. So it's calculated by finding forces in minus forces out. We're going to be talking about 3 different points on a vertical circle. We will be talking about the bottom of the vertical circle. Okay? We'll be talking about the top, where this roller coaster is, on the inside, and talking about the top on the outside. Okay? The forces are different, or they're actually the same forces, but they're aligned differently depending on which of those 3 places you are located. At the bottom of the vertical circle, gravity pulls down. It actually pulls down no matter where in the circle you are. But when you're at the bottom of the circle, down is in or out? Out of the circle. Okay? What force is pushing back towards the middle? Normal force, right? The force from the track is pushing back in. So on that position, Fc equals normal force minus the force of gravity. Okay? We also said that at that point, you feel the heaviest. Because not only is gravity, trying to take you out of the circle, but your inertia is also causing you to push on the circle. The circle has to push back the hardest at the bottom, so that's where you feel the heaviest. It's where you're most likely to black out. If this is something whirling around on a string, it's where the string or handle is most likely to break, because that's where it's under the most duress. Okay? Everybody with me on that? Okay. If we are in this position here, going over the top of the vertical circle, okay, then gravity, as always, pulls down, except that now down is into the circle, okay, and normal force pushes out of the circle. Is there a situation where there might not be any normal force? How would you feel then? You would feel apparently weightless, okay, because you aren't weightless. You feel weightless. Here's a key term that you're going to need to know for this unit. Apparent weight. Your apparent weight is the normal force. You never actually feel your weight. Okay? What you feel is the normal force pushing back on you in different situations. Okay? So sometimes your normal force is equal to your weight, but in lots of situations it's not. Okay? If you're in an elevator and the elevator's going up, you feel heavier. Even though your weight doesn't change, your apparent weight changes. If you're in an elevator and you're descending, you feel lighter. Okay? Your weight hasn't changed, but your apparent weight has, because the floor doesn't push on you as hard. Right? And it's the same as you go around a vertical circle. If we go over the top fast enough, like we saw yesterday, you would feel apparent weightlessness, and thus normal force would equal 0. Okay? In that case then, you only have a force in normal, or gravity. Okay? Now, the other place that we would be looking at would be where the roller coaster currently is in this picture. Okay? And that is on the top, on the inside. So gravity is obviously pulling inwards. Now, is there a minimum speed for this part of the circle? There is. Okay? That's what we saw with the guy running the loop. Okay? If we don't go fast enough, for the guys with the redneck engineering, okay? If we don't go fast enough, then we fall out of the circle. We have to attain and maintain that minimum speed. If we're going just fast enough, then it would be like the Cirque du Soleil guy who was pinned to the inside of the circle, but kind of just fell out near the top. He was going just fast enough to stay in the circle. If that's the case, you don't push on the circle. So the circle doesn't push back. So you would only have a force in gravity. If you're going faster than the minimum speed, now you have more inertia. Do you push on the track? And what does the track have to do? Right. So then you would have an additional normal force. Okay? It's possible to make you feel heavier than your actual weight at the top of the loop. You just have to be going really fast. Roller coasters do this. Very few roller coasters flirt with disaster. Okay? They make it feel like they do, but they don't. Flirting with disaster would be just going fast enough to go through this loop. Okay? That wouldn't be fun. All right? It would be like uncomfortable. Right? You never feel on a roller coaster that goes upside down like you're going to fall out of it. Okay? In fact, you feel pinned to the seat. You actually feel heavier at all points on the circle, but especially the bottom. Okay? So you push on the track pushes on you. Okay? When we used to go to West Edmonton Mall for physics pre-COVID, okay, you could feel this. And at the bottom of this loop, you felt heavy. At the top of the loop, you felt heavy, but you felt way heavier here. Right? Same loop, pretty much the same speed, okay, but you felt quite different between the two. All right? But you never felt like you were going to fall out of the loop. Right? A roller coaster wouldn't be safe if it went that slow.
What about if you were like in a fighter jet and you were doing the loop?
If you're in a fighter jet and you're doing the loop, you need to definitely go fast, especially if you're upside down.
You don't feel the same effect though, because that means you're pushing against
The seat. You're still in a plane, right? So you're still in a pilot's seat. So you're going to push on the seat. Seat's going to push back. Yeah. So yeah, you're still going to feel those G forces that you would feel even if you were at the bottom of the loop. Yeah. Okay. The danger with an airplane is you have to maintain a certain speed, not only for the loop, but in order for your wings to keep producing lift. Otherwise, you'd stall and fall. Okay. So those are the points we're going to deal with. Now, for this particular question, okay. We want to find the minimum speed required for a roller coaster to remain on a vertical track that has a radius of 9 meters. So the only place on a circle that requires a minimum speed is this one, top inside. That's just something we need to remember. Right? There is no minimum speed to go over the top. There's no minimum speed to go under the bottom. Okay? You're just going to naturally do those things. This is the only one where you could fall out. Okay? All right. So if I'm looking at the top of the circle, okay, what we want to do is draw a free body diagram. Okay, as part of our givens. We're at the top of the vertical circle. Okay, we got gravity acting in. We know this is about minimum speed. So there's no normal force. All right, because it's a vertical circle, centripetal force equals forces in minus forces out. Are there any forces out here? There aren't. Okay, so FC equals the forces in. There's only one force in. So what I'm left with is this. mv squared over r equals gravity. Guys, if I'm going just fast enough to stay in a circle, I'm a projectile. And the only thing that makes me go in that arc is gravity. Okay, so the centripetal force is being provided only by gravity if you're going just fast enough to stay in the circle. All right, so I'm trying to find the minimum speed. What part of this am I solving for? Yeah, for V. All right, so I need to get V by itself. M's going to cancel. That's good, because it should be the minimum speed for everybody. Okay, multiply both sides by R, square root. How many times have we gotten that? Square root of GER happens all the time. Okay? If, like, honestly, if on a test you have no idea what to do, try that. I mean, it works like 30% of the time. Okay? Worth a try. Okay. Only if you were like totally lost, if you have no idea. I'm not saying just write it down. Okay, so that's going to be 9.81 times the radius. I think they told us the radius was 9 meters, right? Yes, they did. Just going to be equals. Okay, so square root of 9 times 9.81. Okay, so the minimum speed here is 9.39, 9.4, I think we only have two significant digits, so 9.4 meters per second. Okay, so it doesn't seem very fast, and it's not. And that's why no roller coaster would ever do that. Okay? Like I say, it would not be fun to be on that roller coaster because you would literally fall out of the seat and be against the shoulder harnesses, okay, on the roller coaster. And that's not fun Is it possible the roller coaster could stop there? Well, it would be pretty tough. I mean, we're talking about stopping at the very top peak of a vertical circle, which likely would slide down either side because it's clamped to the track. Okay, but you almost never get something that would stop there strictly on, running out of steam. It is possible for the emergency brake to engage in that position. Okay? And a number of roller coasters have had that happen, where the emergency brake engages wherever the error is detected. Okay, that could be at the top of a loop. Right? We did have one time when we went to West Ed where the emergency brake engaged on the mine bender. And it was like the scariest thing, ever. Okay? And it was right at the very top, right at the start, right before you go down the first hill. And we were going. So we were just starting to go down, brakes go on. And so we're all sitting there like this in the roller coaster, looking at our doom, okay, down that pretty much straight down drop, okay, stuck. Do you think anybody came over the loudspeaker to tell us what was wrong? No. 20 minutes. We sat there. It felt like 2 hours. Okay. I'm sitting in there, Mr. Dickey's in the car ahead of me, and this kid beside me was pulling a full-on Harry Houdini. He was getting out. Like, he had, gotten one shoulder out of the shoulder harness. I'm like, where are you going? I mean, think about this. Look where we are. As much as I don't want to be here, if I get out, I'm going to die. So are you. So sit your butt back down and don't go anywhere. But, I mean, he would have to dislocate his shoulder to get out of this thing. I mean, he was going to. He was going to do a lethal weapon, pop that thing out and go. Okay, but he didn't. I didn't let him. And then they just released the brake. Quietest mind bender ride ever. Everyone was too scared to scream. Everyone's like, get to the end, like, I'm never riding that again. That wasn't any fun. Everybody got off, and then they put the sandbags on and ran it. And we're like, were we just human sandbags? We were just human sandbags. It's the second time I've seen the Mindbender run with sandbags. I don't ride it anymore. I'm too old and I have children. Okay. When you get old, you get scared of stuff that you never used to be scared of. Sucks. All right, so this is what we just did. mv squared over r, we solved for v, okay? We got the minimum speed. All right, so we're going to look at some example problems. So this is what we just did. So we're going to skip that one, calculating minimum speed, okay? All right. No, we just did ones like that. All right, this is the bucket of water question. Okay, so we have a bucket of water that has a mass of 1.5 kilograms spun in a vertical circle on a rope. So even crazier than what I used to do. Okay, so they tie a rope to the bucket and spin it around like this. Okay, so the radius of the circle is 0.75 meters. Speed of the bucket's 3 meters per second. We're looking for the tension in the rope at position C. So bottom of the vertical circle. So in this case, tension replaces normal force because there's no track. Okay, there's no track to push back. It's the tension in the rope that pulls to the middle. Okay, so we're looking for tension. Okay, we can calculate gravity because we know the mass. All right, so give that one a try. Fc equals forces in minus forces out. Okay, give you a minute on that one. Okay, you're looking for the tension in the rope. Okay, so our givens are that we know the mass, we know the speed, and we know the radius. Okay, we know that Fc equals forces in minus forces out. So the next thing I want to do is identify which one's which. Tension is in. Gravity is out. And I'm looking for the tension. So if I'm going to get tension by itself, I'm going to have to add the force of gravity to both sides. So that'll be Fc plus Fg equals T. All right? Now, because I'm saying minus out, I don't have to make 9.81 negative. It's already been given a direction out, and that's been taken into account. Okay, so I've got this formula here. Now I'm going to plug in my formulas: mv squared over r for Fc plus m times g for Fg. That'll give me my tension. Okay, so that's going to be 1.5 times 3 squared, so mass times v squared, divided by r, which was 0.75, plus 1.5 times 9.81. Okay, so 1.5 times 3 squared divided by 0.75, okay, plus 1.5 times 9.81. All right, so the tension in that rope is going to be 32.7. Actually, we only have two significant digits, 33 newtons. Okay, and I should probably say in. Okay. Everybody all right with that? That's how all vertical circular motion works. Identify the forces, okay? Solve for whatever it is you're looking for. They could have just as easily told me what the tension in the rope was and asked me to find the speed, okay, instead, right? So there's lots of different ways for that to go. Okay, so let's have you guys, we're not going to do number 2 because we're not doing the ones that are on the sides, but let's try 1 and 3 here. So number 1's dealing with the same thing we just did, but now it's at the top of the circle. Okay? We're going to say it's still moving at 3 meters per second, even though we know it will be going slower at the top. Okay? We're just going to say 3 so we can save the number. All right, so we're looking for the tension in the rope at position A, top. That's top on the inside. Whenever it's on a rope, there's no outside. Okay, it's only on the inside. Okay. All right, and then number 3 is a separate thing. It's spun in a vertical circle. You're looking for the tension in the rope when the rock is at the top of the, they're giving you, looking for the speed on that one. All right, so we can give you a couple minutes on 1 and 3, okay, and then we'll go over those together. All right, so if we're whirling something around and around in a circle, okay, then we're at the top on the inside of a vertical circle. So we're right here at position A, okay? Obviously, gravity is pulling downwards towards the center of the circle, okay? And what else is pulling? Yeah, tension, because tension substitutes for normal force because there's no track, okay? Now, we have to assume, because they didn't tell us, that this is going faster than the minimum speed. If it was going the minimum speed, there would be no tension. That's like when I was showing you with the tape the other day, okay, the string would go slack, okay, at the top. All right, so I've got those two forces acting in. Is there anything trying to pull this thing out, directly out of the circle? No. Okay, so Fc equals forces in minus forces out, but there aren't any forces out. So we have then that Fc equals the force of gravity plus the tension. Okay? That's why we always say forces, plural, in minus forces out. It's usually just one each, but okay, in this case there's two forces acting in. I'm trying to find the tension. So I'm just going to subtract Fc over to this side. Sorry, Fg, sorry. Now, when I did this for the bottom of the circle, I added Fg. That made T really big. Right? So it makes sense that I should have smaller t at the top. The string doesn't have to pull as hard when gravity is trying to pull it into the middle of the circle as well. So now I put in my numbers. mv squared, my formula is mv squared over r minus mg equals the tension. So that'll be 1.5 times 3 squared divided by 0.75. So there's mass, speed, radius, minus 1.5 times 9.81, mass times gravity. Okay, so 1.5 times 9 divided by 0.75, okay, minus 1.5 times 9.81. Okay, so now there's much less tension. Okay, we had like 20 something, 22 or something like that for the last one. Now it's down to 3.3. Okay, Newton's worth of force. Okay, everybody all right with that? Okay, so number 3, okay, now it's saying it's a rock on a rope, so it's still the same thing we were dealing with. Okay, spun in a vertical circle, tension in the rope when the rock is at the top, so same position we were just dealing with, is now 79 newtons down, so into the circle. Okay, you're looking for the speed of the rock. So same situation, top of the circle, but now we're trying to solve for speed, okay, instead of a force. All right, so on number 3, we're still dealing with the top of the vertical circle. So we got our rock attached to the rope, okay? So we know there's tension from the rope, and we know there's the force of gravity as well, pulling back towards the middle. Okay, that helps us with our FC equals forces in minus forces out. Okay, now that means that FC is going to equal M times G plus the tension. There are no forces out, just the forces in. Everybody with me so far? All right, so whatever this comes out to, it equals mv squared over r. But I'm not trying to calculate what FC is, I'm trying to calculate what the speed is. So I've got this equals this. And I'm putting it in brackets for a reason. When I start manipulating, I've got to bring some of the stuff from mv squared over r over to the other side. But whatever I move over has to be not part of this. Okay? It's going to be in addition to this. So if I'm going to move r over to this side, I'm going to multiply both sides by r. Okay, so r comes over. Then I'm going to divide both sides by m. M doesn't cancel here. Okay, it doesn't cancel because it's not in every term. It's not part of tension. Okay, and this has to be calculated before I do anything else, so I can't cancel the m's. That's really the most common mistake that happens here, is people cancel the m's and they can't. Okay, that gets me v squared. Now I've got v. That is the trickiest manipulation you could possibly run into for this. Okay? And it's just algebra. All right, so what we have is that v equals, was it 0.98 kilograms? Yeah, 0.98 kilograms times 9.81, so that's my m times g, plus the tension, which they told me was 79 newtons, multiplied by the radius, which was 0.4 meters, and divided by the mass, 0.98. Right? So when I plug all that in, I should get 6 meters per second as my speed. Okay? You do have to be careful about how you punch that into your calculator. Okay? I wouldn't try and do it all in one step. Right? I would go 0.98 times 9.81, get that. And then I would add to that 79 newtons. Okay? And then I would divide that or multiply that by 0.4. And then I would divide by 0.98. And then I would square root, rather than trying to do it all in one step. 6 meters per second. Okay? You could try and do it all in one step, but then you got to make sure you get all the brackets right. Right? And chances are, it's easy to make a mistake. Okay? All right, questions on how that one worked? All right, so like I say, these all work the same. All that changes is where in the circle are we? Top on the inside, top on the outside. And then looking for tricky words, like the apparent weight of the person on the motorcycle is 200 newtons. What force is apparent weight? See, I told you that at the beginning. Force normal, right? Okay. If anytime you see apparent weight, they're talking about what the normal force is. So there's those kinds of little tricks that can get worked into a question, but that's really about it. Vertical circular motion always works this way. FC is forces in minus forces out. Figure out which one's in, figure out which one's out, apply. All right, we don't need to do that one. Okay, see how much you remember about artificial gravity. Try question number 1. It's not vertical circle. Artificial gravity is not a vertical circle. Okay, let's see if we can switch gears and figure that one out. Okay, if we're on a space station, we want the centripetal force to feel like what? Gravity. All right, so that means mv squared over r equals m times g. Right? We're simply looking for how fast, or sorry, what its frequency would have to be to simulate gravity on Earth. All right, so we can do this in 2 steps, or we can do that substitution thing, but I assume you probably all did it in 2 steps. Okay, and that is that you solve for v. with that formula, you know, that one that works 30% of the time. Okay, so 9.81 times the radius, which was 30 meters, okay, square rooted would give us the speed. Okay, it gives us 17.155. All right, so 17 meters per second, and then I'm going to go to this. V equals 2 pi r times f. Okay, I could do 2 pi r over t, but then I'm bringing in a whole other calculation after that, and I don't want to do that. Okay, I want to solve for f directly. Okay, so do that, and I've got f, so that's going to be 17 with all the decimals, obviously, over 2 pi times 30, and that'll give me the frequency of the rotation of the spacecraft. All right, so the frequency of rotation is 0.09, okay, or 10 to the minus 10, 9.1 times 10 to the minus 2, okay? They actually have the wrong answer there. It's not the first time. Oh, I know what I did. I put in 17. Yeah, probably the right answer. Yeah. I put in the wrong thing here. Second entry, and I'm just going to go back to this. That number. And then delete that little 7. That's better. Okay. Everybody follow me on that one? Well, then you must have done it okay. It's fine. Yeah, it is fine. Yes, no, okay, this one's a little trickier. Okay, so for this one, okay, I want you to calculate how fast a roller coaster is traveling through a 35-meter loop if the riders feel 2 times heavier than normal at the bottom of the loop. What force do you feel? Which one?
Normal force.
Normal force. Okay, you feel normal force. So your normal force is 2 times greater than gravity. All right? And we are dealing with this point in the circle, bottom. So, what force is acting out of the circle on this one? Gravity. Okay, what force is acting into the circle? Normal force. Okay, so Fc equals forces in, normal force, minus forces out, gravity. Right? That's the situation we're in here. They want to know how fast it's going, so that's going to be mv squared over r equals Fn minus Fg. All right, now, how do I calculate Fg? M times G, right? All right. It says that they feel 2 times heavier than normal. What's 2 times mg? Two mg would be 2 times mg. Agreed? All right. What's 2 apples minus 1 apple? 1 apple. What's 2 mg minus mg? Mg. Okay, that's why people face palm on this one. Okay, if we look at this, we've got mv squared over r equals m times g, because 2mg minus mg is mg. Okay, everyone follow me on that? Okay, that means mass cancels, and oh my gosh!
You're telling me I had it right.
See, if you guessed, remember what I told you. Okay. Came back down to that again. Okay, so square root of, okay, 9.81 times the radius, which was 35 meters. Okay. All right, so it must be moving at 18.5 meters per second. I think we only had 2 significant digits, so we'd say 19 meters per second on that one. Okay? Everybody with me on that?
Yeah.
That's a very common type of question you could get for a vertical circle. Okay, try that one. We haven't had one that's going over the top yet. Okay, so this is now going over on the top on the outside. Okay, so think about what forces are out and what forces are in that position. You are looking for the apparent weight of a 75 kilogram person as they travel over the top of a 150 meter circle at 22 meters per second. Okay. All right, so we're looking for the apparent weight, okay, and this time we've got something going over the top of the vertical circle. That means normal force is acting out, gravity is acting in. Okay? Okay, so we've got, we're looking for, let's see, the apparent weight. So we're looking for Fn. So Fc equals forces in, gravity, minus forces out, normal force. So if I want to solve for normal force, for me anyway, I'm going to make it positive by adding it over to the other side. Okay, so I'm going to have Fn plus Fc equals Fg, and then I'm going to subtract Fc over to the other side. Okay, that way Fn ends up being a positive number. All right, so Fn equals m times g minus mv squared over r. So for this question then, that's going to be 75 times 9.81 minus 75 times 22 squared divided by 150. Okay, so if I'm plugging in my numbers here, okay, 75 times 9.81 minus 75 times 22 squared divided by 150. Right, so we're looking at 4.9 times 10 to the 2 newtons. All right, that's lighter than they would normally feel, which makes sense. If I go over the top of a vertical circle quickly, I should feel lighter because my inertia wants to carry me away. Okay. All right, we'll probably work on a few more of those tomorrow, okay, and then look at kind of doing our final assignment for the first half of this unit before we move on to gravitation. Okay, it's actually more like 2/3 of the unit, but okay, we got gravitation, satellite motion, and gravitational fields left, and that's it. Okay, after this, so it's a quick, short unit. Reminder, your speed and radius labs are due tomorrow, and your centripetal force labs are due on Friday. Make sure you're getting those done.
Okay.